Hello and welcome to Maths with El Profe Lo. In this video we're going to look at the Chinese Remainder Theorem, and we'll give you kind of some background to the Chinese Remainder Theorem, and we'll start with how we could write this system of congruences using words. Alright, so x is congruent to 1 modulo 3, x is congruent to 2 modulo 5, x is congruent to 3 modulo 7. Alright, so how could we write this system using words? Well, the Chinese mathematician Sun Tzu, right, and this spelling will vary depending on your translation, but this Sun Tzu, or Master Tzu, posed the problem as a puzzle. Right? When divided by 3, a number leaves a remainder of 1. When divided by 5, it leaves a remainder of 2. And when divided by 7, it leaves a remainder of 3. Find the number. Okay, so this general method of solving such simultaneous linear congruences in different moduli is called the Chinese Remainder Theorem. Okay, now it is, and I have a footnote here, it is important to note that similar puzzles and problems are also found in old writings from the Indian subcontinent and also from the Greek Empire from the same era. And I've got a couple of links that you can go to find out more about the history of the Chinese Remainder Theorem. All right? But in short, here's what the Chinese Remainder Theorem states. Right? It states that the general, it says that our general method's Chinese Remainder Theorem, and our theorem states that if m1, m2, all the way through m sub r are pairwise relatively prime positive integers, then the system of congruences given by x is congruent to b sub 1 modulo m sub 1, x is congruent to b sub 2 modulo m sub 2, all the way down to x is congruent to b sub r modulo m sub r, has a unique solution modulo this capital M, where the capital M is equal to the product of these pairwise relatively prime moduli. Okay, and that solution is specifically given where x is going to be congruent to the sum from I equals 1 to r of the b sub I, capital M sub I, x sub I, mod capital M. Right? Where m sub I is cap m divided by your particular moduli, and the solution to cap m sub I times x sub I is equivalent to 1 mod little m sub I. Right? So in other words, where m sub I is the product of all of the other moduli, okay, and x sub I is the multiplicative inverse of that cap m sub I. Okay, now this is actually going to be much easier to understand if we work through some practical examples. So let's go ahead and do that now. Okay, so our Chinese Remainder Theorem. Okay, so once again, if we have these pairwise relatively prime positive integers, then this system of congruences has a unique solution modulo the product of these moduli. Okay, so the one that we had to begin with says, hey, x is equivalent to 1 mod 3, x is equivalent to 2 mod 5, and x is equivalent to 3 mod 7. All right, so first, because 3, 5, and 7 are pairwise relatively prime, all right, the 3 and 5 have a greatest common divisor of 1, 5 and 7 have a greatest common divisor of 1, 3 and 7 have a greatest common divisor of 1, so they're pairwise relatively prime, then we will have a solution. Note, because these are prime numbers, we know they're going to be pairwise relatively prime. Okay, so what do we have to do? We have to find big M. Okay, now big M is going to be 3 times 5 times 7, which is 105. Okay, now we also have to find m sub 1, which will be for our first congruence, and that's going to be given by m divided by 3, right? That it's m divided by m sub I. So really it's just the product of all of the other ones. So it's just going to be 5 times 7, which is 35. M sub 2 is going to be 3 times 5 times 7 divided by 5. So it's really just going to be 3 times 7, and that's 21. And M sub 3 is going to be this big M, 3 times 5 times 7, divided by 7, which really is just the product of the others, which is 3 times 5, and so that's going to be 15. Okay, so what we need to do next is solve a new system to find our multiplicative inverses. So in other words, I need to solve 35 x sub 1 is congruent to 1 modulo 3. I need to solve 21 x sub 2 is congruent to 1 modulo 5, and I need to solve 15 x sub 3 is congruent to 1 modulo 7. Okay, so if this is the case, hopefully we can see that by inspection, we have x sub 3 is simply going to equal 1 because 15 is 1 more than 14, which is a multiple of 7. Similarly, by inspection, x sub 2 will also equal 1 because 21 is 1 more than 20, which is a multiple of 5. And for x sub, let's see here, x sub 1, 35 times 1 is going to be 2 mod 3, so that doesn't work. 35 times 2 is 70, and 70 is 1 more than 69, and 69 is divisible by 3, so x sub 1 then would equal 2. Okay? So then our next step is to say that x is going to be congruent to the sum of b sub I times m sub I times x sub I, right? So it's going to be equal to the sum. Well, I have my first, right, and I'm going to have 1, 2, 3 items for my first, starting at 1. Then my second congruence will have 3 items, right? And then my third congruence will have these 3 items for that product, and it's going to be congruent to that modulo 105. Okay, so let's go ahead and do that and put everything in the right place. So b sub I, that's b sub 1, b sub 2, b sub 3. How convenient for us. 1, 2, 3. Right? M sub, we have, cap m sub 1, cap m sub 2, cap m sub 3. So that would be 35, 21, 15. And then we have x sub 1, x sub 2, x sub 3. So that's 2, 1, 1. Right? So that means that x is going to be equivalent to, right? Well, let's see here. If we multiply these things out, let's check this out. All right, what do we have? We have 1 times 35 times 2 plus 2 times 21 times 1 plus 3 times 15 times 1. You want to make sure that you're typing all that in correctly. And there we have 157. So we're congruent to 157 modulo 105. So that is a solution. And the least positive solution would mean that x is going to be equivalent to, right? Well, I'm going to take that 157, subtract 105, and that's 52. So that's going to be congruent to x being equivalent to 52 modulo 105. Now, of course, we can double check our answers and see, does this satisfy our original equation? Okay, well, let's see here. 52 is 1 more than 51, and 51 is divisible by 3, so that works. 52 is 2 more than 50, and that's divisible by 5, so that works. And 52 is 3 more than 49, and that's divisible by 7, so that works. So this is our least positive solution, and that is the approach that we use for solving these linear congruences in one variable for this system. So if I have a system given like this is going to be my solution. These are going to be the items that I need to account for. So I systematically set the information up, work through my algorithm, and get to my solution. Okay. In our next video, we will do the practice problem below. This has been Maths with El Profe Lo. Thank you very much for taking the time.